All right. We started yesterday talking about measurement. You may not have realized it, but what I was basically asking you to do is make some measurements. Right? We were trying to figure out the thickness of a sheet of aluminum foil. There are a lot of reasons why that could be super important. Okay? So these guys happen to work in a sheet metal factory, and to make sheet metal, you take usually large bar stock and put it through rollers that are going to literally squeeze it down into foil eventually if you run it through a series of rollers. But the thickness of the stock going in is really important. If it's too thick, the machines will jam and the whole system will break down, and it'll cost a lot of money to fix, to get everything up and running again. Lost productivity, we won't have good aluminum foil to wrap our sandwiches or do what we want to do. So, measurements and getting good ones and being able to communicate them to other people. Knowing how well you know your measurement turns out to be super important, not only for sort of making aluminum foil, but for all kinds of scientific endeavors. Measurement is really at the heart of the scientific process. Coming up with an idea, testing a hypothesis, fundamentally ends up relying on being able to measure the physical world around us. So we want to set up some sort of way that we can then communicate our findings to other people. So we want to take the time to go through and not get my remote control to work. Probably because the batteries are dead. Oh well, we will adapt. All right. So, okay, that was odd. So what we want to do is we want to take measurements. There are lots of different ways that we can do that. We can use the rulers or the graduated cylinders or the balances you may have used yesterday. You could use a fancy piece of equipment. Okay? In this case, an ultrasonic device used to measure the thickness of pipes by measuring how sound waves bounce off the inside and outside parts of the pipe. And so that device has a digital readout, and it's going to give us some number. Okay? So that number is comprised of two parts. It has the quantity, the actual numerical value, but that is useless without the units. Okay? So this device may spit out answers in inches or centimeters or millimeters or whatever. But unless we know what the unit is, the number is useless. Okay? Using proper units, using units that we can all communicate with is very important. And there's a number of examples that we can find where incorrect units have caused untold damage. For instance, the Mars Observer. It was a British satellite, a joint British and American project, was on its way to Mars and needed a small course correction, as most of those types of satellites do. So the team at JPL put together the amount of thrust. How much thrust did they need? And sent it over to their British counterparts, who programmed that into the computer, sent the commands up to the Mars Observer, hit the go button, and eventually the Mars Observer in a few minutes disappeared. They went through a whole big analysis. Mars Observer cost something on the order of $50 million. And it turns out that the people at JPL had sent over the amount of thrust in a older unit called the foot-pound. And the people at the British team had assumed that they had sent it in newtons. So when they got just that number, they thought it was in two different units, and foot-pounds are orders of magnitude bigger than newtons. So they fired the thrusters way too much. The spacecraft drifted off course so much that they could no longer contact it with radio to give it a new course correction. Understanding units, writing down your units, and being able to convert between units is a key to being a successful scientist. So we all know or have heard of the metric system, System International. It's sort of invented in France a couple hundred years ago. Has a series of base units. Base units are units where we define fundamental quantities. Most of them are arbitrarily defined lengths that we all agree on. This is what we're going to use. So we'll have a base unit for length, which is the meter. Okay? And a meter is currently defined as a certain number of wavelength of a particular color of light. Okay? So we define the length of a meter as, some X billions of wavelengths of a particular color of light. Originally, it was an actual platinum iridium bar, a solid rod, that was created and defined as this is a meter. And you could go to Paris and create a duplicate of that, and then you would say, I know that this is a meter because we've all agreed that this is a meter. Because we all looked at this bar of platinum iridium alloy and said, that's what a meter is. Okay? We can talk about mass. The official sort of unit that we typically use, that you typically see in science, is the kilogram. Notice that there's something a little funny about that. It has two letters, kg, kilogram, right? So we're going to talk about that in a sec. You hopefully have seen that kilo prefix before. So grams are the units, the root of that word. That's mass. And mass is a measure of inertia. Okay? It is not a measure of weight. Mass and weight are technically different. Weight is the attractive force of gravity on an object. The mass is its inertia, how much stuff there is. Okay? So subtle difference that we will almost completely ignore in this class. Okay? So you will see mass and weight used pretty much independently by chemists, because chemists don't do a lot of chemistry, not on Earth. So we can pretty much assume that the gravity is pretty constant. And if you are measuring something where that distinction becomes important, then you probably know enough to take that into account. But in general, we're going to assume that we're on Earth standard gravity, and we're going to use weight and mass pretty much interchangeable. Another one, temperature. Okay, sort of random thermal kinetic energy. The temperature of an object has a base units of kelvins. You may not have heard of kelvins before. They're a lot like degrees centigrade or Celsius in terms of their size, but the 0 point, so 0 degrees Celsius, we all know that's when water freezes. 100 degrees Celsius is when water boils under normal conditions. And so they take those 2 points and divide it up by 100 to get the size in terms of energy of 1 degree Celsius. It's a little bit more complex than that, which we'll talk about in the whole unit, what we're going to do about this stuff. For kelvins, we do something a little bit different. For kelvins, what we do is we say the 0 point is what we call absolute zero. Did that door get locked? Why would somebody lock this door? Is it locked? Yeah. Somebody came by and locked my door. That's very odd. So we set the 0 point to absolute zero. An absolute zero is a sort of special point, the point at which we have zero kinetic energy. And we'll talk more about all this stuff later. And we'll need to look at some conversions between some different units in a little bit. But we'll get there. So we have kelvins. And another base unit, another one that we'll use in this class is time. We're going to measure things. How often does something happen? How long does it take? The base units for time is the second, which is currently defined as a certain number of oscillations in an electron in a hyperfine state of a cesium atom. You don't need to worry about any of that stuff, except to say that we can measure time very accurately using things like atomic clocks, which rely on electron oscillating between two different energy states in a cesium atom. We'll talk a little bit more about that later on. Time is one of our base units, seconds. And finally, the big bad one for chemistry, the mole. Okay? A mole, which we will spend a good deal of time talking about, is a certain number of objects. It's a grouping term, like a dozen. When I say a dozen, what does that mean? What if I said a baker's dozen? That would mean 13. What if I said a gross? A gross is actually 144 something. Okay? There are words that represent groupings of things, grouping of numbers of things. Okay? So, a mole is 6.022 times 10 to the 23rd objects, things. That's a really big number. So, a mole is a very big number of things. A certain defined number, an exact number that we know, or that we can measure, but a certain number of objects, of things. Okay? It's not a mystery. It's just like a dozen, or a baker's dozen, or a gross, or a ream of paper. A ream of paper is, anybody know? 500 sheets. 500 sheets in a ream. A mole, M-O-L, is a 6.022 times 10 to the 23rd. 6.022 times 10 to the 23rd of anything. All right? Don't worry too much about that. We'll get to it. We can do a whole unit on it.
How is that used?
We'll learn all about it. It's not important for right now, and it will take a long time to... I'm going to do a whole lecture on it. Okay? That's just not this lecture. All right, so those were sort of base units, measured quantities or defined values that we look at, that we use to create our derived units. Very common derived unit that many of you used yesterday, volume. Volume is derived from length. Okay? Length. Length times height times width, the three dimensions of an object multiplied together gives us a volume. Okay? 1 liter is 1 decimeter cubed. Okay? What is 1 milliliter? 1 centimeter cubed. And I know a number of you used that yesterday. A cubic centimeter, or a cc. You've ever watched any of those medical drama shows? They'll say, push 500 cc of epinephrine stat. That means 500 cc's is 500 milliliters. So all they're saying is put a volume of some chemical into that person fast. Okay? So, another derived unit is joules. Energy. Okay, we use the value, the unit joules, to measure energy. Okay? 1 joule is 1 kilogram times meters squared divided by seconds squared. This is not that important for you. Using joules is. Energy is critically important to chemistry. How does it drive chemical reactions? How is it produced during chemical reactions? Where does it go? That's all important stuff. We're going to do a lot of stuff using this unit of joules.
So what is it derived from?
It's derived from kilograms, meters, and seconds. Essentially, it's there's a bunch of different ways that we can explain it that we'll talk about later on. We're typically going to relate it to temperature changes, and we'll see that in Unit 6. We'll start to talk about how energy and temperature are related together. The last derived unit that I want you to know about is frequency. Okay? Frequency is a measure of how often a recurring event happens. And the derived unit is the hertz 1 hertz is something that happens once per second. So when I say per second, can you see sort of what that would look like if I were to write down per second? So 1 per, that's like the dividing line, second. So it's 1 over seconds. See this seconds to the -1? What does this to the -1 power mean? Same sort of thing as saying 1 over. Okay? If it's to the negative power, that means it's on the bottom of a fraction. Okay? So we're going to use that a lot, that notation a lot, just because it's easy to type for me. So don't get confused when you see that. If you see something that says like 1 hertz, all that's saying is 1 over seconds. Seconds to -1. It's the same thing. Okay? All right, now we saw this briefly before when we were talking about mass. I said that, remember, we have that kilo thing. This is all stuff I know that every single one of you has learned before. Okay? But we're talking about unit prefixes. One of the cool things about the way the metric system works, it's based on powers of 10. We define a base unit, like a gram. And we say, all right, I want to take that gram and I want to say, well, I have a lot of them. But I don't want to put big fat numbers if I can avoid it. So I'm going to put a little prefix that's going to sort of change my scale. It's going to change the scale that I'm talking about. So what I like to do is I like to use these sort of unit blocks as a way to think about this. Have you ever seen these little blocks, these unit cubes? And then here's a set of 10 in a row. And then here's 100 in a row. And here's a big cube of 1,000 of these individual little 1 block things. So if we say that the little 1 guys is our unit, that's like, say, our gram. Okay? If I wanted to find 10 of them, that would be my decagram. Deca is the prefix we use for 10 of the base unit. So if I had 1 decagram, that would be 10 grams. And I can talk about a hectogram. A hecto of my base unit means that I have 100 of the base unit. So if I have 1 hectogram, I would have 100 grams. And then I could talk about my kilo. If I have a kilogram, that means I have 1,000 of my little base unit. So kilo means 1,000 of whatever comes before. Is this sounding somewhat familiar to most people, hopefully? Okay. We can also sort of reverse this. Instead of saying that this little guy is my base unit, let's say that this big block is my base unit. What if this was my unit? This is now my my gram, okay, or my volume. I can say this is a liter, okay? So if I have a liter and I want 1/10 of that, remember it takes 10 of these sheets to give me one of those guys, this would be my deci unit or my deciliter. It takes 10 of these flat sheets to give me one of those. And then I could say, okay, what if I was talking about these sticks? The sticks are where I want to be. How many of these sticks does it take to make up one of those cubes? This was 10, I'd need 100 sticks, what we call a centiliter. How many of these little cubes would it take to make up this big block? 1,000. So if this is my liter, then each one of these would be my milliliter. Okay? So, if you look on the lecture note handout, you should see a photocopy of a chart in our book. Okay? And that photocopy from the chart in our book has a big fat list of all these things. Some of them are sort of like gray instead of dark black. You need to memorize all the ones in gray. If you don't already know those, you need to memorize all the ones in gray. Okay? So next week, on Wednesday, when we have our quest, I can ask you about any of the ones in gray, and you'll be able to use them because you'll have them memorized. Okay? Now, let's look at some practical applications of this stuff. Does this look familiar to anybody? Yeah, this is your data from yesterday. Okay? What I'd like to do is I'd like to think about and look at this for a sec in terms of the numbers that we put up and some of the stuff we were just talking about. Key pieces of information we want to have on here. Okay? Do you see, and I don't mean, this is exactly what I love. I love this activity because we almost always get examples of things to do and things not to do. So good, centimeters, great unit for this. Millimeters, that's fine. Look, we have this one and this one. Well, we don't have centimeters or meters. These numbers are much less helpful to us. We might be able to make some guesses based on the other ones that we do know, but without the unit on here, it's really hard for us to make sure that we know whether we're talking about centimeters, meters, things like that. Okay? So including units on our numbers turns out to be a really important part of doing the science correctly. Now, we do have a set of different units here. Nobody used inches, which I was very glad about, because we're not going to use imperial English units in this class at all. We're just never even going to deal with them. You don't have to deal with them on any of the tests. I'm not going to make you do conversions with them by and large. We're going to work in the metric system because that's what everybody in science uses, and basically everybody in the rest of the world uses. We do, however, need to be able to make conversions. I want to be able to compare this number in millimeters to this number in centimeters. And that's not necessarily easily doable when they are in these different units. It would be much easier to say, how big is this number compared to that number if they're in the actual same unit? So we want to go ahead and be able to do some unit conversions. Let's say we had one of our values 0.03125 millimeters. And I want to compare that to some value in centimeters. I need to set up a conversion. I need to change the millimeters to centimeters. I know most of you could probably do that in your head. It's just a factor of 10 change. We're going to move the decimal point one place. But I want to show you a process for being able to do that. And the reason I want to do that is because the conversions can become more complex. I wish there was a better way to deal with this board. I don't have it at the moment. We'll look at that in a sec. Everybody, can you sort of see this? It should be on the handout. I think we've moved on to the third page here. So the number should already be on there. So hopefully you can see that there's, it just sort of got mushed up there. Now, what I want to do is I want to go through and I want to set up what we call unit dimensional analysis. Okay? I want to take this millimeters and I want to say, okay, what I want to do is I want to get the millimeters to cancel out and convert into some new unit. So I set up a fraction. I'm going to multiply this number by this fraction. And the way I'm going to do that, I'm going to say, okay, I want millimeters to cancel out. So I'm going to put millimeters down here at the bottom. And I want to convert the millimeters into centimeters. So I'm going to put centimeters on the top. For every 1 centimeter that I have, how many millimeters does that represent? 10. Okay? It's a 1 to 10 ratio. So now I've got a setup here where I can go through and say, oh, look, the millimeters cancel. I need to take this number divided by 10 to get my answer. I can get 0.003125 centimeters. I converted the millimeters into centimeters. Well, now that's just ridiculous, isn't it? You better make that correction on there. Good catch. Thank you. Yeah, it looks like the my lecture handouts have a typo. That happens. Okay? Fairly straightforward. I believe most of you have probably done stuff like that before. If you haven't, don't worry. We are going to practice that a little bit. I know that's what you're looking forward to. Okay. So, our scientists working at the foil factory have measured the aluminum foil. Okay? Unfortunately, they're in America, and they made their measurements in inches. So the aluminum foil that you used yesterday should have been about 0.00064 inches thick. What would that be in centimeters? What piece of information do we need to know to be able to do that conversion? We need to be able to know the ratio of inches to centimeters. That turns out to be a defined value. The length of an inch is currently defined as a certain number of centimeters. Does anybody know what it is? 2.54 exactly. Okay? 1 inch is 2.54 centimeters. If that is true, how thick was the aluminum foil? Take a second right now in your example box and work it out. You might want a calculator. We had our 0.00064 inches. We're going to set up the conversion to do that. I want the inches to go away. I'm trying to get rid of the inches, so I put the inches on the bottom. And what am I trying to get to? Centimeters. So I can go ahead and set up that ratio. I know for every 1 inch, there are 2.54 centimeters. So then it's now just a math problem. And I can get that it is 0.0016 centimeters. And that is the actual sort of standard value for normal aluminum foil. Should be certainly very close to what we had for our aluminum foil. You should make sure you get that down, okay? Because I'm going to ask you to do some calculations with that tomorrow. So you've got that value. Now, notice my number here and this number here. Okay, 64.0016 centimeters. Now, if we come back and take a sec and look back at some of the values that you guys collected, some of these, 0.0037 centimeters, 0.0038 centimeters. We're certainly not outside the realm of possibility there. Obviously, these were fairly crude measurements that we were making. Some things I have a little bit of a question about. This is going to lead us into our sort of next thinking. But if we look at, say, this number here, so this is in millimeters. So, if we wanted to convert it again, we'd have to divide it by 10, so that would push this decimal point out one more place. But look here, this is 1, 2, 3, 4, 5, 6, 7, 8 decimal places out. So 8 decimal places out in millimeters is getting us down to the tens of nanometers. What we have with this number, what we're writing here is that we know to within a few atoms how thick the aluminum foil is. You think our measurements were that good? No, I don't think so. I would doubt we'd even have 2 significant figures here, 2 digits. So one of the things that turns out to be super important when we're trying to share information with people is that we are accurately describing how well we know the measurement. I don't want to say that I know to the tens of atoms how thick the piece of aluminum foil is. And I also don't want to say that I don't know very well. In general, getting more accurate, getting more decimal places on your measurement costs money. And if you made a measurement that has a lot of decimal places, you want to show that. You want to say, I know this number really well because I use really expensive equipment. Okay? Or I made very good measurements. Okay? I conducted a really good lab. So you want to be able to accurately reflect, how well do I really know this number? And to do that, we are going to introduce the idea of what we call significant figures. In other words, limiting how many of these decimal points we write down to what we can actually know. And this is going to create a fundamental schism in how we do math in this class versus how you do math in your math class. In math, you almost always work in the realm of idealized perfect numbers, where the decimal places can go on for infinity. Okay? That is not true in science. The numbers that we use are measured values. Okay? We used a piece of equipment to measure them. If you used one of the rulers that was only marked in centimeters, and I put some of them out there, you may have seen some of them that only had centimeter marks and no little tiny millimeter marks, you're going to get a different one than if you used one that was marked in the millimeters. One of the balances I put out would measure to the tenths of grams. The other balance I put out would measure in the hundredths of grams. The price difference between those two is about, the one with the hundredths of grams is about twice as expensive as the one that only measured to tenths of grams. Okay? So we want to accurately reflect those pieces of information. To do that, we need to understand what parts of the number we consider significant, that is carrying useful information, and which parts don't. We have to be able to count the significant figures. So, fairly straightforward. There are a few simple rules. Okay? Here is a number. We have a number 0.0210300. This number contains all the different types of possibilities that we might run into. First, if it is a number that is not 0, it is by definition significant. Everything that is not 0 is significant. So the rest of the rules deal with the zeros. And there are 3 categories of zeros. There are what we call leading zeros. Leading zeros are the zeros in front of the non-zero numbers. Anything to the left, any zeros to the left of all of the non-zero numbers are by definition not significant. Why are they not significant? Because I can get rid of them. I can rewrite this using scientific notation. Does anybody remember scientific notation? I know you've used it before. It's where we use powers of 10. I want to move this decimal place. I'm going to shift it 1, 2 spots. I could rewrite that number as 2.10300 times 10 to the negative second. Because this number is less than 1. Okay, so I want to shift the decimal point. When I multiply this back, the negative would shift the decimal point to the right. Okay, so leading zeros are never significant. They do not carry useful information. They are placeholders only. Okay, they're just so that we're in the right columns. Now, second category of zeros. That's an always sort of situation. A captured zero. A captured zero is the zero that is in between non-zero numbers. Captured between 2 non-zero numbers. Captured zeros are always significant. So we have leading zeros, which are never significant. Captured zeros, which are always significant. That leaves us with our trailing zeros. Trailing zeros, zeros that are to the right of our non-zero numbers. And we go, okay, that's good. And we say, uh-oh, it depends. Trailing zeros are significant if there is a decimal point in the number. if the decimal point is written, that means it doesn't have to be less than 1. It could be a number greater than 1, but the decimal point is put down. Then the trailing zeros are significant. Okay? If there is no decimal point written, then the trailing zeros are not significant. They are placeholders only. They help us just get to the right spot, to the left of where the decimal point would be. So, for instance, this number has 1 significant digit. This is the only significant digit. This number has 5 significant digits. Trailing zeros depend on the decimal point. The whole point here is to accurately reflect on the measurements. Okay, accurately reflect on the measurements. How much time do I have? Not very much. Okay? And the devices we use are going to round off these numbers in different places. Okay? Either us looking at the balance or us making measurements with the rulers. Rounding is going to have to take place. And that's why we need to limit how many digits we write down. Okay? So, next example. How many significant figures for each of the following? So there's another example box on the back, page 4 example box. And I have 4 examples. How many significant figures for each of those examples? Okay, these are, what kind of zeros are those guys? Captured zeros, they always count. How about this number here? B. 3 significant figures. Okay? Leading zeros, these zeros to the left, never count. This is captured, it counts. There's our 3 right there. And in C, 4 of them. So we have 2 captured zeros, a 1 and a 3. Why does this 0 not count? No decimal point. Decimal point is not written. If the decimal point were written, then it would count. But it's not, so it doesn't. Finally, the last one in D, how many do I have? 5. 1, 2 captured zeros, 3 0. This 0 counts this time because the decimal point is written. There's a decimal point written with the number, it counts. Okay? Now, we can count, look at a number, and figure out how many sig figs it has. But you did math yesterday in the lab. Most of you, many of you did some sort of math. Some of you did some dividing. You may have done some addition. We need to track how these significant figures flow through calculations. Okay? 3 basic rules. If you are doing multiplication or division, you look at which number has the least number of, just the total number, the least number of significant digits. You don't care what their decimal point is. You don't care. If I punch this into my calculator, okay, if I punch this into my calculator, I get 2.5. Can we sort of see that? So I get an answer of 5.0125. But this 2.5, I only really know it 2 digits of it. So in my answer, I can only really know 2 digits of that value. Multiplication and division, it's the number of significant digits that are important. I round off so that my answer has the same number of digits as my least significant answer. The real answer in chemistry is 5.0. Okay? If I do addition and subtraction, it's what decimal place am I at that's important. Not how many digits there are, but the actual decimal place. numbers of significant digits, but the decimal place remains important. So if I add up these two values, this 4.95, I have to think about what's my least significant decimal place. I do not know what this number is. It could basically be any digit 0 through 9, which means that when I add it, I don't know what this one is. So I look to my least significant decimal place, my least precise, in this case, the tenths place. I have to round my answer off to the same decimal place as my least precise number. In this case, this one rounds off to 5 as well. Last thing, what if I want to do both? I go through and I do the math in the correct order of operations. I do not do any actual rounding until the very end, but I keep track of the significant figures as I'm going. So when I am doing this addition problem, 2.8 plus 3.29, I know that that adds up to 6.09. But again, I know this to the tenths place and this to the hundredths, so my answer really would have been rounded off to the tenths place. How many significant digits exist in this number? 2. I've written 3 numbers down. I'm going to continue to do the rest of the math with all 3 numbers, but I must remember or note down or keep track of this really only has 2 because now I'm doing a multiplication problem. And in this multiplication problem, it's not the decimal place that's important, it's how many are there. So when I go through and get my answer of 64.980, the last step was multiplication. This one has 4 significant digits. This one has 2. So my answer should have 2 significant digits. I need to round off